Hi, this is a video about analyzing accelerated motion to help you prepare for this coming exam. I'll try to make this as quick as I can, but I wanted to introduce you to one last thing to make this analysis more interesting. Specifically dealing with this problem here about the minivan that accelerates onto the freeway. This I think people have been finding pretty straightforward, and this is just calculations. I would direct you to CAM5, which looks like this. CAM5 is kind of our connection between the graphs and algebra. We haven't talked about this in class, but this is where it comes into, like, you'll see how this becomes really important when you start trying to do algebra using these values. What I wanted to show you is just two things. One of them's small and one of them's kind of a big deal. This is the small thing, the idea that when we're making a table, we don't necessarily have to fill in all these values for this to be helpful. It helps kind of like get our thinking in the right place to know that this is going from 0 meters per second to 20 meters per second, which is the information I got from here, in 14 seconds. That is, having the velocity value table gets us in the right place, and we can tell that 2, 4, 6, 8, 10, 12, like we can actually do some division and say, like, what are these divisions that will work in a constant acceleration way? What is the increment that this has to go up by every second, every 2 seconds, in order for it to reach 20 meters per second in 14 seconds. You don't have to fill in this whole table with every number. You don't have to say 0, 1, 2, 3. That's not necessary. It's just a place for you to think about how to do the problem, how to analyze the problem. Next thing I want to show you is how this connects to the graph. We know, of course, that this thing speeds up, so it would go from 0 to 20 meters per second in 14 seconds, which could look like this on a graph, and then it stays at that constant speed of 20 meters per second for the next 3 seconds. We know already from the work that we've done before that the area enclosed by this graph will tell us the displacement. That is, this question here, determine the distance from the stoplight to the speed limit sign that the car passes at 20 seconds into the trip. We know that area is a good way to calculate that displacement. So in this case, the area consists of a triangle that is 14 seconds of base and 20 meters per second of height. You can figure out the area of that triangle using your triangle formula, and a rectangle which consists of 6 seconds of width and 20 meters per second of height. Both of these can translate into displacements that you can then calculate as part of your total. We didn't take any notes on using triangles, but those of you who have been paying attention recognize that you can record notes on your own in CAM9. I'm not going to give you any notes to record here, but if this idea is going to be helpful to you on the test, write down an example right here to show you how to do it so that you're using your notes on the test. One thing that I do want to show you that is pretty complicated is what's called a derivation, and if at any time during this video you're like, what's going on? That makes no sense to me. That's okay. You don't need to know this. It's just another representation, specifically another algebraic model for dealing with constant acceleration situations. I want to show you where it comes from, and then I want to show you the final example. If we start with a graph that looks like this, which is a velocity versus time graph, we have a initial velocity, and we know that the slope is the acceleration. I'm just going to show you a couple parts of this because we now know that the displacement that we can calculate here can be broken up into two parts. Delta x, that is the displacement from the triangle part, that is this part right here, and also delta x from that little rectangle part. We can show with no numbers at all only letters, how to calculate both of these using algebra. So for example, it looks like this. Delta x rectangle, which I'll do first because it's easier, delta x rectangle is equal to the initial velocity, that is the height of the rectangle, times the time interval, that is how much time this thing is moving at exactly that speed. That we have seen before. This is slightly more complicated, and I could get into the details of how to show it exactly. But what I want to suggest is that, well, I'll do this first. The rectangle looks like this. The rectangle has a height of v initial, that's v sub I, and a width of delta t. That's where those two numbers come from. In order to calculate delta x triangle, we need to first envision what that triangle looks like. We know that this triangle also has a width of delta t, but the clever thing is, the tricky thing is here, is we can actually figure out, and we can show this to be true, that the height of that triangle is equal to the slope times delta t. That is, acceleration times delta t tells us how much this thing has sped up. For example, if the acceleration is 1 meter per second, and the delta t was 3, then it would go from, I don't know, 2 meters per second to 3 meters per second to 4 meters per second. That is, it would change velocity this much. So if we want to figure out what the total height is of this triangle, we can just multiply these two numbers together. This is important because if we're actually trying to figure out the area of that triangle, we know we have to do 1/2 base, which in this case is delta t, times height, which in this case is acceleration times delta t. What this gives us is the following. Delta x triangle, that is delta x from this accelerated part of the graph, is equal to 1/2 acceleration times delta t squared. You'll notice, because I think you've seen already, that if we try to make a position versus time graph of something that's accelerating, we see curves. These curves are parabolas, and they come from the fact that there is a t squared in the displacement calculation. That is, when something's accelerating, the effective time is squared. It's not a linear relationship. The effective time is squared, as we saw when we calculated that. So what I want to show you is a general equation for calculating displacement when acceleration is constant. We still have the area method. We still want to use the area method just like we used here. But if we use this general equation, it'll work out also. And the general equation looks like this. Delta x equals the initial velocity times the time interval plus, that's from the rectangle, initial velocity times times delta t, plus 1/2 acceleration times delta t squared. That's the part that's from the triangle. That is, we took these two parts, this part that we calculated and this part, and we added them together. And what this gives us is a situation where if you wanted to calculate how far this thing went while it was accelerating, you could use this equation directly. You can calculate it using the graph, which is actually my preferred way to do it. But if you want to just use algebra, you can use this algebra. Notice there's supposed to be space here for an example, and I've given you just a little bit of space here to actually plug some numbers in. But you will find, if you try the numbers from this problem for just this triangle part, you will find that using this equation gives you the same number as calculating the area of that triangle. That is, this equation, if you keep track of your positives and negatives and you keep track of what's going on, this equation will tell you the same answer. And of course it should, because those things need to agree with each other. Those multiple representations need to be consistent. So if you want to try preparing to use this equation on like this problem with the minivan, which is problem number 2, and this problem with the minivan where the minivan is slowing down, that's going to be important, thinking about whether acceleration or velocity is negative. One of these is going to have to be negative for question number 1. Showing me that you've learned, that you've in fact taught yourself how to use this will be an even more special thing on that goalless question at the end of the test. Keep in mind, of course, what I said at the beginning of the section. If what we just saw here was really confusing to you, you have a choice. You can either go back and watch this video again, practice it hard, really work with it, spend some time with it, and show me that you have done that. And I will reward you for that with points on your test, and just like recognize that you're doing some impressive science on your own. Or you can always say like, I don't feel like doing that much, thanks very much, and just stick to the area method. Know that this type of question that we didn't talk about in class at all, this type of question is going to be necessary for you to get a 4.0 on this test. To really separate out the people who are getting a B in this class from the people who are getting an A in this class, I need to see that you have thought about how to do these difficult problems. And part of that is getting older, seeing how science works when your science teacher isn't telling you how to do everything. A lot of people have stepped up to that challenge, so congratulations. Use your notes. Take it easy on this test. Give yourself the time that you need, and use your notes carefully in situations like this so that you have examples that you can refer to as you do this work.